Chaos in the matrix, the anatomy of raw pigments. Raw pigments are solid crystalline particles that naturally tend to clump together. Left untamed, they cause mechanical weakness, color loss, and poor gloss in the final polymer. In this process, we deal with two types of clusters: aggregates, which consist of strongly bonded primary crystals that require intense shear force to break apart, and agglomerates, which have weaker bonding forces and are larger in size. Although agglomerates are easier to break, they must be fully dismantled for a truly uniform dispersion. The impact of particle size on performance. Particle size is the ultimate driver of performance. As particle size decreases from microns down to nanometers, performance metrics like tinting strength, mirror gloss, and hiding power reach their peak. The core insight here is that optimal dispersion isolates individual primary crystals. Achieving a tight, standardized particle size distribution unlocks maximum color depth, saves expensive raw materials, and maximizes mechanical stability and UV resistance. The dispersion mechanism, a three-stage pipeline. The pigment dispersion mechanism follows a structured three-stage pipeline: wetting, replacing trapped air with the liquid medium, driven by surface tension and capillary flow. Separation, mechanical milling to break down agglomerates and aggregates using shear stress and impact. Stabilization, preventing re-aggregation through steric or electrostatic hindrance. Wetting and surface tension. To wet a solid, the liquid surface tension must be lower than that of the solid. Lowering the contact angle towards zero enables critical capillary flow into agglomerate crevices. Solvent systems like xylene, butyl acetate, and white spirit easily wet most pigments due to their low surface tension. However, aqueous systems present a significant challenge due to the high surface tension of pure water. They require highly active surfactants to drop surface tension and force capillary action, especially for hydrophobic pigments. Mechanical separation. During mechanical separation, intense shear and impact forces fracture particles down to target sizes. But this creates a critical vulnerability. The moment particles fracture, entirely new, unwetted surfaces are exposed. This becomes a race against time. The liquid medium and dispersants must instantly coat this newly exposed surface area. Any delay allows particles to crash back together, exponentially increasing the required milling time and energy. Stabilization mechanisms. To counteract persistent London attractive forces and prevent re-agglomeration, we rely on two primary mechanisms. Steric hindrance. Polymer chains absorb onto the particle surface, creating a robust physical, solvent-soluble barrier suitable for both water and solvent-based systems. Electrostatic hindrance creates an electrical double layer where particles with the same charge repel each other. This is primarily used for inorganic particles in water-based systems and is sensitive to pH and salts. Combining both mechanisms is known as electrosteric stabilization. The dispersant arsenal, molecular weight framework. Dispersants are categorized by their molecular weight framework. Small molecules, surfactants, MW between 300 and 2000, offer high compatibility and are broadly used in solvent and water-based systems. Oligomeric dispersants, MW between 1000 and 3000, feature multifunctional anchor points, making them exceptional for universal tinting pastes. High MW polymers, MW from 5000 to 20,000, linear or branched chains with numerous reactive anchor sites that deliver superior, heavy-duty stabilization for demanding industrial environments. Advanced polymer architectures. Advanced dispersant architectures come in four specialized designs. Polyacrylics, linear backbones that unlock extremely high pigment loading with narrow molecular weight distribution. Polyurethanes, branched structures optimized for drastic viscosity reduction in solvent and 100% solid systems. Star polymers, core shell geometry with a dense, pigment-loving core and outward radiating chains for extreme stability. Block copolymers, CFRP, distinct organized blocks of pigment-loving and solvent-loving segments that outperform traditional homopolymers. Dosage strategy. The formulator's diagnostic guide. Required dispersant volume directly scales with the pigment's specific surface area or oil absorption value. Inorganic pigments. Require 10% of their oil absorption value. Carbon black. Requires 20% of its oil absorption value. Organic pigments. Require 20 to 25% of their oil absorption value. Formulation nuance. Standard organics typically need 50% of the calculated additive, whereas specialized copper phthalocyanines require only 25%. Validation. Proving the matrix. To validate dispersion quality, 3 testing protocols are used. Storage stability testing. Samples are held at 50 to 60 degrees Celsius for 2 weeks to detect slow reaggregation by monitoring viscosity, tinting strength, and gloss. The drawdown test provides visual and instrumental comparison of gloss, hiding power, and color depth. The rub-out test. Friction is applied to a semi-dry film. Any distinct color shift confirms pore stabilization and pigment
migration.
Diagnosing defect, flooding and floating. When stabilization breaks down, unanchored pigments migrate, leading to severe visual defects. Flooding. Vertical separation through the film thickness, causing surface color to drastically differ from the bulk material. Floating. Modeling. Horizontal separation across the surface where pigments organize into localized cells, creating streaks and a mottled appearance. Root cause. Incompatible dispersant choice, insufficient dosage, or failed steric electrostatic barriers. The golden rules of formulation. To conclude, keep these 4 golden rules of formulation in mind. Organic versus inorganic. Inorganics are chemically easier to wet and disperse than organics. Allocate milling time and budgets accordingly. Respect the shear. Shear-sensitive pigments like metallic flakes will fracture and lose brilliance if overprocessed. Scale translation is critical. Lab milling must strictly mimic the thermodynamic profile of production-scale extruders or paint mills. Source verification. Pigments with the exact same name from different suppliers or with different surface treatments require complete re-optimization of your dispersant package.